Hello everyone and welcome to the 8th lecture of the information visualization course. Today we are going to be talking about graphs, networks and trees. So that means that we're gonna discover how to visualize handling data with important explicit relations between data points. And today's theory is heavily based by a paper by Tatiana von Landesberger and collective. So that's a useful optional reference for you to go to summarize this, what we've been talking about mostly. So if we go back to data typing, types of variables that we might encounter in visualizations, trees and networks are considered one of the 7 basic types of data. So it has been in the eye of InfoVis since its inception pretty much. And the following section is meant as a bit of an inventory of graph terms and terminology. So if you know this like the back of your hand, which you might as a computer scientist, then please bear with us. You can space out for now. And come back later. But let's just do a bit of an inventory of basic graph theory terms and naming conventions. So what is a graph? Graph is a set that consists of a set of nodes, which is denoted V usually because they are also called vertices, and the set of edges, which is those are connections between the nodes that define relations between individual nodes. So here we have a basic example of a graph with 6 nodes and 3 edges. This is the foundation of the graph theory. Graphs can be directed or undirected. So on the previous slide, we have an undirected graph because we don't specify which directions the connections go. They go both ways. In a directed graph or digraph, edges have orientations or directions. So you go from 2 to 1, but you cannot go from 1 to 2. You can also have bidirectional edges, such as the one between node 0 and node 2. In the kind of directed graph representation, elements of E, so edges, are ordered pairs. That's the difference between the representation of a directed and undirected graph. As in undirected, elements of E or the edges are unordered pairs. That's the difference. And I mean, in the following slides, I will always expand the notation, like how would a graph that is on the right side, how is it going to be encoded in the actual data. You can also have typed nodes or edges. So both nodes and edges can be of various types. In our abstract example here, we have 2 types of nodes, the white one and the blue one. And we also have 2 types of edges, which is the black one and the orange one. This will of course have some sensible semantic meaning in InfoVis applications, but I think it's a simple enough concept that we can keep it abstract here. You can also have weighted nodes and edges. So nodes and edges can have different weights, and here we have again further developing our example. Our representation changes. So each node is going to be the node ID itself and the weight. For instance, this is an example representation how you can represent it. The data structures can be different, of course. So node 0 has a weight of 2. It's also drawn with the bigger size, and node 1 has a weight of 1. So weight of 2, 1, and so forth and so forth. Similarly for edges. So here I have depicted it with the thickness of the line. A common convention is also that you write the weights near the node. So this would say 1, this would say 2, 2, and 1 again. Then we also have the concept of a tree. So a tree is a special case of graph in which any 2 nodes are connected by exactly 1 path. The alternative definition of a tree is that it's a graph with no cycles. Here we have an example of a tree. This, even though it doesn't look like one, is a tree. It can be redrawn as this, which is the more traditional / useful look. Depends how you look at it. Then we have the term network. So this lecture is titled Graphs, Trees, and Networks. So there's a bit of a term discrepancy between graph theory and InfoVis. In graph theory, network is a directed graph with weighted edges, whereas in InfoVis, network is any graph with attributes associated with nodes and edges. So with type nodes, weighted edges, and you can also have other attributes associated with your either nodes or edges. So basically, whenever you have attributes, you don't have the vanilla graph. It's considered a network. So it's a bit of a terminological shift. So be mindful of that. Another term that is important is the compound graph. That is a tree combined with a graph. I think the visualization here speaks for itself. So we have have this little graph, and the blue edges constitute a tree within that graph. So that's called a compound graph. Why is it specifically useful? It will help us aggregate because you can go from nodes to groups of nodes, and then to groups of groups of nodes, or groups of nodes and edges, basically of level 2, 3, and so forth. So it will help us aggregate, and it will help us in zooming in our visualizations to have a compound graph. Then there's a so-called dynamic graph. So a dynamic graph is a graph that can have typed and weighted nodes and edges, and in addition to that, it can evolve over time. Changes can occur in types, weights, and also other attributes of nodes and edges, and edges can be also added or removed altogether. These aspects can be combined freely, but the key is that the overall node layout doesn't really change. So this is a graph at a certain time step, and this is a graph at a different time step. So this denotes change over time. So we see that the node, for example, node 0 has changed its type to blue. The edge between 0 and 2 has increased in weight from 1 to 2. It has become unidirectional from 0 to 2, and it changed type to black, and so forth and so forth. I mean, I think it's obvious we don't have to go over all these little changes. Dynamic graphs are very, very interesting for visualizations because they are significant for when you have temporal data. So this could be, for example, places in Amsterdam that can have some kind of relations, maybe flow of people, and it will evolve over time. And this used to be a cafe, so that was a white node, and now it's a restaurant, so it's blue. And you have different, for example, movement patterns over time, which you might want to visualize. So dynamic graph is a very important variant of graph for InfoVis. To briefly summarize, so graphs can be split or categorized into two categories roughly. One is based on time dependence. Static graphs stay the same over time. Dynamic graphs change with time. They can change pretty much everything except of the overall layout, the nodes. Then we have then we can categorize by structure. So we can categorize this into graphs or networks in the InfoVis sense. Trees, which are a special case of graph, and compound graphs, which are combinations of graphs and trees. Example of graphs for better illustration. You can, for example, if you plot relationships between people, such as this example from the popular show Game of Thrones. You have a graph here, so you have arrows. So the nodes are individual people, the edges are their relations. Here you have an example of typed edges, because the relations are different. So somebody can be someone else's son, somebody else's brother or sister. So those are different types of edges and instantiation. The classic way to describe relationships, so while we're at human relationships, is the family tree. Here we have an example of the family tree of the Dutch royal family. This is also a graph, right? So you have nodes that are the stations. We have seen this map of London Underground in lecture 2. And here we have typed nodes and edges, right? So the edges are typed by the actual metro line. So that's the That's the type of the edge, is the metro line, and you have I see now it seems to be stuck a bit. Oh yeah, sorry, it got a bit of a lag at my computer, and we also have typed typed edges, because some of the stations are transfer stations where you can change from one line to another, and some of the nodes are just stations on one line, so you cannot change there. So this is a transfer station, one type of node, and this is non-transfer station, another type of node. This is also a very familiar visualization. It's a file or / directory tree, and those are trees those are actually trees, and that means that they are graphs as well. And another example, a bit more complex one, is we have seen this system before, and we're going to see it towards the end of this lecture. Is that you can these are migration paths between the cities in the United States on the map. So this is also an example of a graph visualization, a bit more advanced one. Tree visualizations or graph visualizations can also look like this. So here we have this is the so-called radial layout. We're going to go over this in detail in a couple of slides forward. And so this is a graph of citation patterns of papers across all scientific fields. You can check out the full visualization at the link given on the bottom of the slide. So okay, so we have graphs. We now have a bit of a sense of how graph data looks, what it can be useful for. So how do we actually visualize it on the screen? So it's very important to actually analyze and filter graphs because small graphs can be obviously just directly visualized on the screen, as you have seen on the previous slides. I have shown a small graphs with a couple of nodes and edges, no problem. But those were kind of trivial lecture examples. So what about large graphs? I mean, before we go into what is into how do we visualize large graphs, it's valuable to understand what does a large graph entail. So if you have had graph theory before, possibly maybe some AI on graph data, the algorithmic analysis of graph data is usually well performing these days. But large graphs are those that have very long computation times or intractable computation times and or too large memory footprint or that this constitutes a challenge. In InfoVis, a large graph is anything that leads to clutter. So that's a very simple concept. And from my experience, large graphs from the InfoVis point of view tend to be much smaller than those from the analytical / AI point of view, because the reason being that we need quite a lot of screen space for a single node and its edges. So if you remember a scatter plot, a single data point is just one dot on the screen. Whereas here, if you have this kind of classic node link way of displaying graphs, as we have seen in the previous slides, then you need the node and you need also all of its edges. So that's considerably more pixels for just one node than you had for just one data point in a scatter plot. And the result is that this clutters very, very fast. If you have a graph with 100 nodes, it's already quite a challenge to visualize directly. So it explodes very fast. So the question is, how do we reduce the size for display on the screen? And in the following section, we are going to go over a couple of basic techniques to facilitate this. So the analyzing and filtering is a part of the overall pipeline that we should follow if we want to go from a raw graph to a visualization. So the main passage is like this. So we have a graph, we analyze it, we filter it, and then we visualize it. That's the ideal state. Sometimes if we filter it, then we go to wholly new graph that we then want to analyze further slash verify if our filtering didn't lead to data distortion or incorrect conclusions, basically, or incorrect forms of the graph. And of course, we can alternate between filtering and analysis. Those two are often done hand in hand and iteratively. So this is the overall pipeline from graph to a visualization, which we're going to follow. And again, like this is going to be a second quite shorter part of terminology inventory for graphs, because we're going to use these terms further. So again, many of you might know this very, very well, but let's go over this anyway. So what do we mean by graph size? So graph size is the cardinality of the set of edges, so the size of the set of edges, or the number of nodes simply. And useful measure is graph density. So that is the number of edges relative to the number of possible edges between the nodes. The formulae are slightly different between a directed and an undirected graph, namely ×2 for the undirected graph. So you don't really have to remember this from memory. I mean, it's nothing difficult, right? So for a directed graph, you put the number of edges into the numerator, and the number of possible nodes is the number of vertices times the number of or edges times the number of nodes times the number of nodes minus 1. And this is twice as much, because in an undirected graph, each edge goes both ways. So it's not a very, very difficult or arcane concept. Why is this useful? It's very important to identify graphs that are complete, where everything is connected. So that means the density is 1, or the so-called cliques. And cliques are subgraphs that are a complete graph. So if part of your graph is a complete graph, then it's a candidate for filtering, as we're going to see in a second.
Could I ask something?
Yes, absolutely.
Can you? Yeah. Can you? Oh wait, you're not on the. Wait, hold on 2 seconds. Can you have over complete graphs if you have like two like edges, but one has like a different weight, for example, and then you could have more.
Yeah, so you can we are not gonna, like, for the purpose of this lecture, we are not going to consider basically graphs that are connected by multiple edges. That's of course a part of graph theory. So here we simplify a bit. So here we are discussing basically only graphs that have one edge in one direction, basically. So and we kind of hide the possibility of over-connected graphs by the fact that, okay, if it's a stronger connection or like a double connection, then it's like a different type of a connection. So it's a bit of a simplification. You're absolutely right.
Okay. Yep.
Yeah. So yeah, this is a valid remark. So all of this that we are saying, this is a subset of graph theory, of course. So I don't presume to explain the entire graph theory in the first couple of slides of one of the lectures in InfoVis, right? So indeed, we are simplifying here. Then we have the notion of a degree. So degree of a node is simply the number of edges incident to the node. And again, in a directed graph, in undirected graph, it's simple. In a directed graph, the degree is a sum of a so-called in degree, so number of edges directed towards the node, plus out degree, which is the number of edges originating at the node. So why do we need this? So why is a degree interesting? Well, nodes that have either a very high or very low degree tend to be interesting, right? So, for example, if you would have migration patterns, or you would have movement of people across venues in Amsterdam, then those nodes that and you will be let's say in the hospitality industry, so it's going to be, I don't know, restaurants, cafes, places like that. Then those cafes that are very popular are going to be nodes with a high degree. They have lots of edges coming in. Whereas if you look at the nodes which have a very low degree, those are establishments that are not visited by anyone, right? So already this is an application of graph theory which is useful for visualization. So if you're visualizing graph data, especially on a map, but not exclusively on the map, it's this is a very useful analysis to kind of to see where you have your kind of clusters where people or where your data tend to congregate, the influential nodes, and which ones are more isolated. Data structure is one of the analytical or / high level tasks that we defined in the interaction lecture. So if we look at this example graph, a very simple one, here we have the degrees spelled out. Then here we see that the degree of node 2 is 3. So everything seems to be coming to node 2. So this could be an interesting node, whereas node 4 doesn't have any edges. So that one is interesting as well. So why is it so isolated, right? So, but formally this is called a degree of a node. So one method, a simple one, but it works surprisingly well. One method to reduce the size of a graph is called stochastic edge sampling, which is a fancy name for removing nodes randomly. So you just say, okay, I'm going to randomly select X nodes from my graph to remove. You're going to of course, you're trying to have this number as low as possible. So if you randomly remove 9 nodes out of a graph that has 10 nodes, then it's probably not very correct. But if you can slightly reduce the size of the graph, and then it's feasible to put it on the screen, then stochastic edge sampling it could be a way to go for you. So if you remove the nodes, that will of course automatically remove all corresponding edges, because an edge has to go from a node to a different node. It cannot be hanging in the air, so to say. So you're going to do that. Alternatively, you can just remove edges. So you leave the nodes as they are, and you just remove edges, because sometimes you can have enough screen real estate to display the nodes, but you might be running out. But you might have all those little crossings that are annoying to look at, that are cluttered. So then you might just want to randomly remove edges. It's a very simple method, and it approximately preserves statistical properties. So if you're doing the stochastics right, and if you are truly random in your selections of edges / nodes to remove. This is a bit of a reminder slide. We have already talked about geodesic distance in our multivariate data lecture. But to recap, geodesic distance is
2 more minutes or 3, whenever you can run.
Okay. It's the sum of edge weights along the shortest path between 2 nodes. And if you have an unweighted graph or all your weights are equal, then you can replace sum with count. So you just count the edges along the shortest path. So again, here we have a couple of example distances, geodesic distances for this graph. And geodesic clustering is again a method to reduce graph sizes. So the name of the game is finding a set of representative nodes, such as the geodesic distance of all nodes to the representative is minimized. Here we can see a graph with quite some prominent cliques, right? So this is a clique. This is a complete graph of size 6, and this is also a clique. So it's a complete graph of size 4. And so if you're choosing representatives and we're discarding the rest, it may be good to choose point A, because it's close to the rest of the graph, and it's very well connected. Whereas if, for example, from this clique, it's bad to choose L, because it's on the outer boundary of the clique and connected to the rest of the graph. So we might want to go for E instead. Yes, I'm gonna do that later. Are there any questions at this moment?
At this moment, no, there are no questions.
Very good. So let's take a 5-minute break, and I'm going to see you soon. All right. So let's continue. Were there any questions in the break?
In the break, there were no other questions asked, only before, but I'm not sure if it was a question. Somebody said directions is not recorded in slide 7, I think. Perhaps some mistake on the slide or so.
Okay, I'm going to take note of this, and I'm going to review the slides and correct any mistakes. Thanks for the remark. Okay, so we've been talking about methods to reduce size of graphs before we put them on the screen. We talked about the stochastic edge sampling. We talked about geodesic clustering, and let's continue with the methods. Another method that is called structure-based filtering is that we remove based on connectedness. The idea is that we remove edges such that any two connected nodes remain connected. And the key observation is that in a creek, you can remove many edges and in many different orders, and things will still stay connected. So I mean, so of course this is not very suitable for cases where shortest paths are supposed to be immediately visible, but for approaches where this is not of paramount importance, this can be a thing. So, for instance, if we are removing here, we first remove C to H, because we can still reach from H to C via A and B. Then we can also remove B to C if we want to. I mean, then it's a bit of a journey, but then we cannot remove A to B anymore. So if we remove C, if you want to go from H to C, and we have removed this edge and this edge, then we're going to go here, and then here, which again, it nicely illustrates the problem of the shortest path. So this remains connected, but you know, it's a much longer path than it used to be. Whereas in the creeks, we are a bit more free to remove, as the coherence is going to be very strong, even if we remove a couple of edges from here. So it's an option, but it will distort the view of shortest paths quite considerably if we opt to do this method. These have been the really basic graph filtering methods. And here is a bit of a visualization to illustrate this. So here we have the original cluttered graph. I mean, all of them are kind of cluttered still, but this is the most cluttered. That's the unreduced graph. B is the stochastic edge sampling. So we have randomly selected nodes and edges to be removed. This one has been done with geodesic clustering, and this one with structure-based filtering. So various methods result in different outcomes. So they provide a bit of a different view of the data, which is kind of similar to similar effect to what we have seen in dimensionality reduction methods. How different methods led to different visualizations. So if we are losing information, then we are of course introducing a bit of data distortion, which will also result in these differences. So we can and should filter, but we have to be careful. Alternatively, so if we go beyond the basic methods given in von Landesberger 2011, we can have approaches that are minimum spanning tree based or Pathfinder network. So what these are? I think these are more structured approaches that are less random and feel less arbitrary, definitely. So first, what is a minimum spanning tree? So if we have a connected undirected graph, a spanning tree is a subgraph that is a tree that connects or spans all nodes. And a minimum spanning tree is a spanning tree with minimal sum of edge weights. So you can intuitively you can consider this a skeleton of the graph, if you will. So basically, the minimum spanning tree method is simple. You find the minimum spanning tree and you just show the minimum spanning tree on the screen. So you reduce this original graph to which is the black plus the gray edges to just the black edges. And you preserve the number of nodes. So this just reduces the number of edges. It doesn't reduce the number of nodes. Alternatively, you can do the Pathfinder method, It's again a geodesic method, so we're again utilizing geodesic distance, and it's based on the notion of triangular inequality. So which says that direct path between two nodes should be less or equal to a sum of a path through a third node, basically. So for any, so this is the mathematical or pseudo mathematical expression of this concept. So if the inequality is violated, we remove the offending edge. So here we have two examples. So in this mini graph, everything is okay. So if we choose a path between any two nodes, that weight is always smaller or equal to the sum of going through the third node. So 2 is less than 4 plus 3, 3 is less than 2 plus 4, and 4 is less than 3 plus 2. Whereas here, if we have a graph like this, then the AC edge is offending because 8 is not less than less or equal to 3 plus 2. So here, this is a path that will realistically never be taken. In, let's say, so we can reduce it. We can cut this this node and basically just keep this. And basically in the final graph, so if we proceed like this, if we iterate over the entire graph, then all paths between pairs of nodes are going to be the shortest path. So it's a Pathfinder network can be viewed as a bit of a generalization of MST. So these two, so the MST approach and the Pathfinder approach are very structured, and you see that it's less random. It focuses on actual inherent properties of the edges. So it might be worthwhile to check out. And of course, we can reduce clutter by aggregation. So we have talked about compound graphs. So indeed, if we have a structure like that, that we have nodes, groups of nodes, and groups of nodes, then we can use this, and we can with our scroll wheel we can zoom in or zoom out, reducing clutter. So aggregation is almost always a good idea if you can achieve that. You can do this through, for example, hierarchical clustering, but there are other methods. Sometimes it's a direct property of the data, but aggregation is always a very powerful technique for clutter reduction as well as interaction. So there's the abstract elaborate interaction, if you recall. Okay, so those have been those filtering methods. But how do we draw graphs actually on the screen? So we have our graph that is now suitable to go on the screen. And we want to draw the classic visualization that you see below and that you have seen on most of the previous slides, and that is called a node link diagram. So it's the name is very simple. These are nodes, these are links. So it's not called a node edge diagram, which could be a bit more accurate with respect to graph theory. It's called the node link diagram, but that's the terminology. And we need to determine the layout, because I can place all these nodes any way I want. So this is not the some kind of default ordering. I could move node 4 here, and it would be a valid node link diagram for the very same graph. So we determine the layout. How do we draw the nodes based on the attributes? So we can have typed nodes. So we can have a different shape, color, texture, or size. And how do we draw the edges? So that is the question. And I mean, we can split our problem into two categories. The first is the georeference data. So we actually have, for each node, we have the geo coordinates. Then the task is very simple. We just place the nodes on the map, and we combat clutter by, for example, by aggregation. That we don't have too many of those nodes drawn in a specific region. And but otherwise, we are, of course, free to position the nodes as we please, and the optimal positions in that case are determined by various aesthetic criteria. I think that the best breakdown has been achieved already in the 1990s by COSAC and Collective. So here we have rules that we want to adhere to when drawing our graphs. Going over it very quickly, or node link diagrams rather. So going over it quickly, we don't want to have the nodes overlapping. We don't want the edges or the links intersecting with the nodes. So we always have a bad example and a better example, and I think it kind of speaks for itself. So if we can, it's best to align everything in line. Symmetry is very pleasing to the eye, so this goes even back to the Gestalt laws. Zoning, if you have different zones or subgraphs that are significant, it's best to split them if you can. A T-shape is usually best if everything is regular. I think it's a bit weird. It's called T-shape, but you know, make it nice and regular here. Try to draw regular polygons if you can. Reduce the number of link crossings. I mean, here this is a bit of a representative example for it to have small nodes. I don't think that a graph like this is a big problem, honestly. But if you have bigger graphs where you have lots of link crossings, it's still good to minimize the number of link crossings. So you know, personally, I view these two as equivalently pleasant. I don't really mind this one, but I mean, again, this is InfoVis, so opinions may vary. But from a general standpoint, in a general abstract graph, this is definitely a rule to follow. So I'm not disagreeing with what they have written here. Evenness of link lengths. So it's if you can afford it, regular nice shape, and sum of link lengths. I think that this refers to the fact that even though this is a nice regular shape, then you still kind of want to collapse it a bit so that all of these are a bit more even. So I think it kind of relates to the previous rule, unless I'm interpreting this wrong, but that's how I understood this rule. So these are related. So yes, we're gonna have problems with size. So we have already talked about this before, and it's quite common that many algorithms that work with hundreds of nodes, which itself is very difficult to draw on the screen, as I have put before. Those will fail on 10,000 nodes. So we have to be. So size is indeed an important factor. And if we're thinking about good information visualization on graphs, there can be we can think about scalability in three modes or three kind of levels. One is in the number of nodes. So a visualization is scalable with nodes if it remains readable with increasing number of nodes. Then we have in number of edges. I mean, this is a nice example why you shouldn't Control-C, Control-V. So indeed, it remains readable even with increasing number of edges. So if you increase the number of edges, and in number of graphs. So sometimes you can have multiple graphs that you want to show, maybe even a lot of graphs, and then you might need your visualization to be scalable in even if you add entire graphs. So scalability doesn't relate or doesn't pertain strictly to the graph size, which has been defined as the number of nodes, but it can relate to nodes, edges, and even entire graphs. So we have to be careful about that. And some general considerations when designing a graph visualization. So of course we want to reduce visual clutter. That's a no-brainer. And here we have the same problem as with regular data. So we have had some techniques for clutter reduction in lecture 3, I believe, which all of them remain valid for graphs. But with graphs, the problem is a bit exacerbated due to the existence of edges. So you will not only have those individual points, but you're going to have connections between them, and they might need separate treatment. We also have to reduce what is called spatial aliases. So those are visual elements, or in this case, nodes or edges, that might be mistaken for different ones due to their placement. So you will confuse nodes because they're close to each other in the visualizations. Then of course, we want to maximize compactness. So we want to use our space and time efficiently to display the data. That's more of a generic InfoVis rule. An important one and an interesting one for graphs is predictability. So if we run our placing algorithm on the same data twice, then we should have identical results, right? So we should end up with identical visualizations. But this can be a problem because some placing algorithms start from a random initialization. So then you obviously will end up with a different graph. Then there are also considerations called dynamic when we are placing nodes on the map. So we should preserve the mental map. So mental map is the imagination of the user or of the reader of our visualization. So the given structure that we draw on the screen should support a natural kind of abstract structure a user forms looking at the graph. So the way this rule is written in the literature is a bit confusing because it sounds so arcane, right? It's like so the given structure should support a natural abstract structure. Well, so what is that actually? Because if we know some kind of natural abstract structure the user forms in the brain, then we just draw it like that, right? But this abstract structure is never given, or it can differ between users. So how I interpret this from the practical point of view is basically don't obstruct inference and analytics. So don't try to be too fancy with your visualization, like imposing some kind of structure to being drawing something fancy that you think encodes a lot of useful information. But if a user actually looks at it, then they are confused because they cannot work with it very natively. So this is the user friendliness rule, or that's the way I interpret it anyway. Then we should also reduce cognitive load, which is another user friendliness rule. So we should not overload the working memory of the user, and the user. So we show as little information the user needs to keep to actually read the visualization. So we are not trying to be too fancy, too fancy again. But this rule relates tightly to the things that we have established in the perception and cognition part of the course. So this is just a reiteration that this applies fully. And we have tried to minimize spatial aliases, and we want to minimize temporal aliases. So you can confuse visual elements, nodes, edges, not only due to spatial arrangement that they are displayed on the same part of the screen, but they can be placed similarly in time, or for example on an axis. So we don't want to confuse nodes because of their temporal placement. So that's a different type of these aliases. And so the main class, or generally how node link diagrams are being drawn on the screen, those are called force-directed graph algorithms. So the idea is that it's if you have ever seen a spring and mass experiment in maybe your high school physics class, it's the same. It's the same thing. So nodes connected to each other will attract each other spatially, so as if there's a spring between them, and unconnected nodes repulse each other. So imagine this as if a mass would be hanging between unconnected nodes. So basically, node 4 would be a mass hanging on node 2, and these would be the springs that connect node 2 to nodes 0, 1, and 3. And so it looks like it looks like this. So there's also going to be a weight here, and of course the weight is inversely proportional to the distance. So the closer you are, the more you're trying to pull away, but the further you are, the further you are, the more you stretch these springs, right? And the less pull those unconnected nodes are going to have. So these are the springs. So the edges are the springs, and the unconnected nodes in the vicinity are the masses that pull those pull the node away. And you do this for every node. And force-directed graph algorithms aim to optimize uniform edge length. So there are often additional constraints being placed on the length of the edges. So you are trying. So if you have an edge, especially of a similar weight, you really want to keep the lines roughly the same size. And symmetry, a very pleasant thing to have, as we have discussed, is optimized as well. Generally, all of these algorithms work. This is a very pseudo code. So we will initialize nodes at random positions. This is exactly the problem with predictability. Maybe you can tackle this with fixing the random seed beforehand. And then we basically, what we do, until convergence, we repeat that we compute all forces between nodes. So we are going to take into account the springs and the masses, the weights, and basically compute a vector, the pull vector for each node, and we're going to move all nodes in a small step in their preferred direction, and then we're going to iterate until this settles down. So it's a similar logic to the k-means clustering algorithm, if you know that one.
I also want to say we have about 3 more minutes or 2.
Okay, very good. Thank you. There are 3 main force-directed graph algorithms. They are all named by the people that have created them. The EATS algorithm is the oldest one. They use so to compute all those forces, they use electric style formula, so electric force style formula for repulsion, but spring force for attraction. So they decouple the energy from the spring mass in the kind of physics sense. So the spring force for both, they replace for repulsion, they replace this with the electric force-esque formula. Kamada and Kawai further adapt the algorithm such that the distance between nodes in the visualization should be proportional to the length of the shortest path. So you know, that is related to the minimum spanning tree, or to the Pathfinder algorithm that you really want to, that you kind of have the skeleton of the graph where each each node pair, the path on that Pathfinder is the shortest path. So this is quite related. So you're not trying to you're trying to kind of keep the overall structure of the graph given by the shortest path between pairs of nodes. And Fruchterman and Reingold further improves the ease distribution of nodes. Again, we're not going to go over this in a true math sense. So you can, if you're interested how the actual algorithms really work, this is a high level overview. You can go over these key terms and you will find the exact formulae how things work. And here's a bit of an example how those algorithms work. So this is a randomly drawn node link diagram. This is if you employ Kamada and Kawai version of the algorithm of the force-directed algorithm, and this is Fruchterman and Reingold. I think we can stop here. Are there any questions at the moment?
No, today not so many. There are still no questions.
Today not so many. Okay, but so if anybody comes up with questions, please feel free to. We're going to answer them like always, and let's have a break and see each other in 5 minutes. All right, so let's continue with the lecture, unless there are questions coming from the break. We have been talking about how to determine the layout of a node link diagram, and we have discussed the class, or I've given a high-level overview of the force-directed algorithms, which is the main technique used to place nodes on a map or on the canvas, rather, in the visualization when working with node link diagrams. Also, you can so if you want a bit of an interactive example, you can try it out yourself. There's a D3 example under the link I have in the first bullet point, and also, and if you want to just see a video, then follow the YouTube link. Okay, so now we have done all the prerequisites. So now let's finally start talking about how to visualize graph data. What are the visual representations used? The two major representations are, well, the node link diagram that we have already seen, and also the adjacency matrix. So a bit more about the adjacency matrix. We have explained the node link diagram before. So adjacency matrix is V times V matrix. So the number of nodes times the number of nodes, because both rows and columns are nodes, and individual items in the matrix depict edges. So so here we have our nodes that are typed, as we see. So we have violet or magenta nodes, yellow nodes, cyan nodes, and black nodes. So this allows us to encode typing and weighting. On the diagonal, we map the nodes again for a bit more visual clarity, and and here this item means that the second magenta node is connected to the third one with the gray connection, basically, or gray type connection, and so forth. So you can do this for each item away from the diagonal. So this is a very compact representation of a graph. And here we have this nice conceptual depiction of how do we move from a node link diagram to the equivalent adjacency matrix. I think this is a very nice representation. So and indeed there are things that you quickly learn when reading adjacency matrices. So if you see something like this, then it's typically a clique. So this part corresponds to this clique of size 5, and so forth. So here we have the kind of the beam style connections that we have a very central node, and that is connected to many edges, and those edges are not connected to anything else. That will appear as long rows and columns, for instance. So there is some intuition behind it, so one needs to learn how to read those adjacency matrices. But if you have seen a couple, then these strong visual artifacts are gonna come to you. So it's a bit of an acquired taste, but it's a very compact representation of graph data. So those have been the two main representations for the generic graphs. But if we're talking about trees, then our technique palette is much more wider. So McGuffin provides a nice decomposition or nice categorization that we're going to follow, and we're going to go over each of these classes in detail. So I mean, the first two are kind of clear. So those are node link diagrams again. So we're not going to spend too much time on that, except that usually a tree in a node link diagram is drawn with the root node up, and we progress towards the leaves on the bottom. But this is at this point in your studies, this is, I guess, so intuitive that we really don't have to spend so much time on this. So let's jump straight to the icicle plot. The name is evident. It looks like icicles hanging from the roofs in winter. The root node is up. Leaves are towards the bottom. And what happens here is that it's a space filling visualization, where each of these levels is the level of the tree. So this is the root node. This is level 1, level 2, level 3, and so forth. And the width of each node encodes the size. So if you have weighted nodes, or if your tree is some kind of, let's say, market share, or you're trying to you're kind of decomposing your data into sized sections, then icicle plot is a very useful visualization, because you can easily encode size of each of those subtrees by width. So for the root node, the width is of course 1, so the entire canvas. So the root node fills the entire canvas, and here we now see the proportions between between the children and their corresponding subtrees. So that's the nice part about the Icicle plot. The next class is the radial node link diagram. So we have a node link diagram like usual, and the root node is this time at the center, and each successive layer is on a concentric circle one step further. So these thicker let's say thicker edge, or it's direction of not edges. So these thicker lined circles that kind of are concentric and expanding from the center, those are actually not edges of the tree, but they are denoting the level in the tree. So the edges are these the actual present edges are these little lines that go across these concentric circles. So we have the president, then there's the vice president, secretary, office management, vice president for production, treasurer, and for finance, and then we expand the company tree more towards the edges of the circle. So what is really nice about the radial node link diagram is that trees will typically expand in node count with increasing depth levels, right? So on the root level we have one node, on this level we already have 5, and we have more and more nodes the further we go in total on the depth level. So it's always like this triangle, right? If we're looking at tree visualizations. And radial layout is very suitable for this because each circle further from the root is more spacious, right? So there is less space on this circle than on this circle. So basically you're expanding, in a way you're expanding your canvas the more in depth you're going, which is very nice, because if you're going to be drawing a tree on a rectangular screen, then that one has fixed width, so you're kind of wasting a lot of space at the top. But here, when you're going to have 100 leaf nodes, then you will have problems filling the or like fitting rather on the rectangle. So you waste a lot of space. So this is a bit more efficient, and it takes advantage of there being more space in each successive levels. So that's quite a nice property of a radial node link diagram. An example of this. So there's this. It's actually one of the mini benchmarks for graph or tree visualizations in InfoVis is the Flare ActionScript class hierarchy. It's a bit of a meta benchmark, because the Flare used to be a library, a very popular library for actually creating web visualizations, and that one had a lot of classes that were organized in hierarchical structures. So this is the entire library, Flare, and there have been classes in the Vis category, util category, scale, query, physics, and so forth. So to actually test if the visualization is suitable, the visualization designers were using the class structure of that library because it was a very familiar data set. The classes were very familiar to intermediate to advanced visualization designers, so they were quickly able to see if the visualization they design makes sense. So this is a radial node link diagram for this ActionScript. So if you can actually see, it has also been used here. So this is also Flare. You see Flare, Vis, util, animate, query, analytics, and physics, and so forth. So this is again Flare. So if you're gonna look into these graph visualizations, you're going to see Flare. You're going to see it a lot if you Google it a bit. So it's exactly that. Further, we have the Sunburst chart or Sunburst diagram. I have even seen Sunburst plot. The keyword here is Sunburst. Well, even that not so much like radar chart / star plot. This is called Sunburst. Some people call it Starburst. So but let's stick to Sunburst for simplicity. It's pretty much a space filling variant of the radial node link diagram. So it's a bit of a pie chartization of the radial node link diagram, but that's a possibility for instance. Here we see a coffee tasting diagram. So coffee has tastes and aromas, and each of those are separated. So if you're some kind of coffee expert, then you're going to be categorizing the taste of coffee into these groups and subgroups. So this is a visualization of that. You can see it in greater detail following the link below. Then we have the nested circle diagram. So that's quite an old technique already, but quite usable. So here we see that here we have a root, and we see a bit of a we see we see subtrees that are bursting from the center, and each of those nested circles. So here the circles are implicit; they're not actually drawn. So the nested circles are actually the little imaginary circles around each of these trees. Are also trees / graphs of their own. So this is also very useful to display compound graphs. And what you can do is that if I'm here at the root and I'm interested in, let's say, this subtree, so then I can, with interaction, I can typically click, and then it will expand. So the root of this subtree becomes the focus of the entire view, and then I can maybe hit some kind of back button to go back to the top of the hierarchy. So this allows quite some nice zooming and elaboration. So this is actually the example that we see here is actually not this one, but it's if I'm interested in this one, then it will expand into this, and I can go further down. So it has this nice kind of top-down view in a radial layout. It's very good for aggregation. It's an interesting technique for that, definitely. And then we have the tree map, which is a very classic visualization, which I believe is best explained visually. So suppose that we have a tree like this. And this border is our canvas. So this is our screen within which we are trying to visualize this tree. So what happens is that you start at the root node, and you see that it has 3 children. So I'm going to split the canvas with into 3 parts: 1, 2, and 3. So 1 and 2 are leaves. So those are visualized directly. So this is 1 and 2. And then when I move to 3, then so that's this part of the screen. Then I'm splitting it again, and I'm alternating between horizontal and vertical splits, because otherwise it would be not as nicely readable. So I have 2 children, so I'm going to split like this. Again, then I inspect the children. So this is 4. That's a leaf. So I'm gonna draw the leaf directly. And 5 is again a root node of a subtree. So this is my design space for 5, which I'm going to split into 3. So 1, 2, 3, or rather 6, 7, 8, and those are already leaves. So I'm going to display 6, 7, 8. So the tree map actually directly visualizes only the leaf nodes. So it's not very suitable if you want to emphasize on the intermediate nodes. But you can always see the intermediate node kind of implicitly, right? So node 0 is the entire canvas. Node 3 is the respective part here, which mark. Node 5 is this part, right? So this is how you construct a tree map, and how you read a tree map. And it's quite an old technique. So we can even call it the mother of space filling visualizations, or rather graph visualizations. The size of nodes is this time encoded as areas of the respective rectangles. So this is very useful for data where your leaves are the actual nodes of interest, and they have different sizes. So it's a very nice visualization for that use. Do we have a question?
Yeah, like Jan asks, it's from slide 46, so a bit earlier, I missed that. Is it better to avoid clutter by showing only half the adjacency matrix, as in the triangle, because it is symmetric in the diagonal?
Yes, so a very good question. So for the undirected graph, it's you can easily show half. But if you have a directed graph, then you need to show both, because it doesn't have to be symmetric along the diagonal. So if you're going to say that the direction has to say, okay, I'm going from here. I'm going from here. So this is the origin node, and this is the destination node. Then it will not necessarily be symmetric along the diagonal. So then you need the entire matrix. But it's a very good question. I haven't talked about this indeed.
All right, thanks.
Okay.
And Lianson asked if there is any tool available to interactively update a graph and or tree, possibly node link visualization for both nodes and edges.
Yeah, so I'll admit I'm a bit light on tools when it comes to graphs because I'm not working with graph data myself in my practice too much. So I know the theory, but I'm not a great practitioner. I think Georgi and Inske are actually working with graph data, so it's best to ask them, I would say.
All right, thanks.
Okay, so excuse me. Where were we? At a tree map, yes. So tree map is the classic space filling visualization. We're not drawing the intermediate nodes. And when we're drawing, then it's very important to alternate between vertical and horizontal splits, because otherwise we're going to have ever narrowing long slices. So we want to avoid that. Tree maps are of course very similar to Icicle plots, because the difference is that Icicle plots encode sizes as lengths, which is better than areas, admittedly. So here we are encoding as areas. Is the area of the rectangle. In an Icicle plot, it's the width. So Icicle plots are better in this regard, but tree maps are more screen space efficient. So we have seen that a tree map. So if this is our canvas, it will very nicely fill the canvas. Whereas an Icicle plot, going a bit back, you see we're wasting quite some space here for the same kind of tree. So yeah, that's the difference. But both are very viable. So you can use either. To give you an example, a very popular early example of a tree map is called Smart Money. This visualizes stock data, where each small rectangle is let's say is a top or a very prominent company, whose size is proportional to the company's valuation. And the green color means that the prices were going up, and the red color means it's going down. And the neutral color, the neutral color is black in this case, so not white but black. And here we see, so it gives us a beautiful overview of various industry sectors, and we see that in 1998 the energy company stocks were quite hot. Many of them were going up, whereas transport, as we see, so there are some companies of non-trivial sizes, so it's not a very small company. There are smaller companies here, small rectangles. We're not doing so great. So this is a very nice overview of stock market data, for instance. And to the best of my knowledge, I think that Wall Street people have actually been using tree maps, or are using tree maps, some of them still, for exactly this kind of analytics, which is very nice. Another nice example is so-called Sequoia view, where so this is a visualization of somebody's hard disk. So each of those rectangles is a file on the disk, with and the file type drives the color. So this is actually encoding categories. So it can be a video, a library, a text document, and whatnot. So this is for example very useful to diagnose, like, do I have some big files on the disk that are not doing that much for me, which if I delete them I will save space. So I mean, of course there are tools for this in modern operating systems rather, sorry. And but this is a very early example. So this is a system from, I believe, 1999. So it was quite ahead of its time then. And here, this is a nice example of data where you're actually interested in leaves, and the intermediate nodes don't matter at all to you, or not so much. So because if you think about it, like if you want to save space on a disk, you're deleting individual files. I mean, you can of course delete directories. So if I have a big directory and this is one directory, then I might delete all of it. But the actual building blocks are the files. So the directory doesn't incur storage space needs on its own. It's the files that are contained the directory. So this is a very nice use case for a tree map. And finally, we have the indented outline visualization. We have already seen this, and you have seen this a number of times in your previous practice. It's, for example, file and directory trees are displayed like this, where each successive depth layer is indented, which indicates nesting, or it indicates the layers of the tree. And you can easily use the collapse and unpack interaction here. So that's an instantiation of abstract elaborate, like these little minus and plus buttons. So those are very useful, so that you're not overwhelmed by the structure down to its leaves. So this is a very simple but powerful visualization for trees as well. Alternatively, so we have followed one possible taxonomy. Alternatively, you can consider dimensionality. So is it a 2D visualization, 3D visualization, or a hybrid? You can split trees by edge representation. So explicit, are we visualizing edges directly, or implicit, which means that you use mechanisms such as inclusion, overlap, or adjacency to implicitly show edges. You can also have a hybrid there. And finally, node alignment. So is the plot radial, that we have a circular arrangement of the tree layout, so to say, or circular layout, or do we have a rectangular arrangement, which is called axis parallel? Or again, we can have a hybrid. Speaking briefly about 3D visualizations, we haven't touched on that topic. Yes, it's a viable alternative, but again, is the same as with other 3D visualizations. We need rotation, so you need to be able to rotate this for best analytic performance.
3 more minutes.
Okay. And so if we use the alternative taxonomy, we can, for example, if you have plots such as the space reclaiming Icicle plots, which is recent work, then we see that this is two-dimensional. It has implicit edge representation, so edges are not drawn explicitly. We see that they are implicitly drawn by the successive levels. So basically, all the nodes in a certain layer are connected one level above and to the respective nodes below. And the node alignment is axis parallel, because this is a a perpendicular or rectangular arrangement. Conversely, the sphere tree is a 3D visualization, so it's a sphere. The edge representation is explicit. We see those little lines that go there, so we draw the nodes. Draw the edges as lines, so that's explicit. And the node alignment is radial. It's a sphere, right? What is nice here is that if you go to treevis.net, it provides a very nice survey of various tree-based approaches that you can inspire yourself by, and it uses this alternative taxonomy. So 2D 3D hybrid representation. So implicit so alignment is radial or axis parallel, or hybrid, or we can representation of edges explicit, implicit, or again hybrid. So I have checked it. It still works, but it will complain about expired SSL certificate. But to the best of my knowledge, it's safe, so it shouldn't pose a security risk to your machine. Let's take a break here. So are there any questions so far?
There was still one question by Jansen, who asks, how do you choose between the different types of tree visualizations? What criteria should one consider?
Right. So it depends, right? So we're still gonna show some techniques for especially radial visualizations to combat clutter. So the picture is not complete yet when it comes to the argumentation, but it's basically what's useful to you, right? So for instance, we have given a clear indication when you should use a tree map. So if you're not that interested in drawing the intermediate nodes very strongly, and if you're interested in the leaves mostly, such as in the file disk data, then a tree map is a great visualization. tree maps and especially Icicle plots are very good if you're interested in sizes of the individual subtrees, because they will nicely give you the split. And radial slash node link, it's I would say that a classic node link diagram is fine in general, but you will run into screen problems. So one of them I have already illustrated, that if you draw the classic tree, you will waste a lot of screen space at the top, and you will not have enough space at the bottom if you're drawing trees. Whereas with the radial layout, this is a bit alleviated. So each of those has certain nuances, and it really depends on your data. So it's because the problem with graph data, at least for me, is that the structures can vary massively. So you know, the theory is a bit abstract, and then you typically take your data and you see what works best for you and your purpose, basically. So here I'm just giving a couple of techniques with some strong and weak points of each. But I'm not sure if there's like a strict non-fuzzy decision diagram which you kind of, or flow chart that you go from start and then you pick the correct visualization at the end. It depends on the data a lot. Yeah. Okay. So
all right, thanks. That's it with questions for a moment.
very good. So let's take a 5-minute break and I'll see you soon. Okay, so let's wrap the lecture up. We're going to, okay, so we've been talking about trees in the previous section, and now a couple of words on compound graphs. So again, to bit of a reminder, compound graphs are a combination of a graph and the tree, which is very useful for us because visualization-wise, we can use the tree for structure. So we are kind of determining the hierarchy and enclosure, and then we take care of the remaining graph edges. So if we have a so this is an example of a compound graph that has kind of like 3 components. We can structure it by the skeleton tree. So we can, for example, find the minimum spanning tree to determine the skeleton, and then we can plot it something like this. So we're gonna have this is a nested circle graph in a way. So if you have a generic graph which is not a tree, you can still maybe take advantage of the tree visualizations, which are a bit more plentiful than the classic graph visualization, because those have been the node link diagram plus adjacency matrix. Those are the two by far the dominant ones here. Or with trees, we have seen some 9 variants of tree visualization. So if we kind of make a compound graph out of our regular graph, then we might harness the tree techniques for our generic graphs. But there is a problem, of course. So because the edges in a tree visualization generally go from, if we have a radial layout, it goes from center outwards. So we have our root node here, and we're only gonna have nodes going like this. But in a compound graph, of course, edges are also going between the nested nodes. So we can have edges going from here, and it's a big cluttered mess. So this is the same compound graph. On the left we see nested circles. On the right we see adjacency matrix. A bit stylized, but it's still an adjacency matrix. So how do we do this properly? Because yes, this is pretty cluttered. And the answer is that if we have a situation like this, we can bundle edges together to create a smoother flow. So details are in the paper by Danny Holton that is linked below. But the idea here is that we have this so-called bundling strength parameter, which is if it goes between 0 and 1. I mean, again, the paper has the full math, so you can compute it exactly for your graph. But 0 means that you're not bundling edges at all, and 1 means that all edges are bundled. So and the bundling is that if edges go from, and the bundling means that if you have edges that go from similar regions to that originate in similar regions and go to similar regions, then you're kind of bundling them together as one edge. And this is and you can do this in a continuous manner. So we see a nice progression from completely unbundled through a couple of intermediate steps to fully bundled. So, and this of course clears up the clutter considerably. And finally, I'm going to give an example of an advanced system here. So that's the multivariate network exploration and presentation by Stefan den Elzen and Jarke van Wijk. That one, I think, won the best paper award at IEEE UvA in 2014. So the advanced system trope is not only my judgment, but also a judgment of the community. So we have seen this screenshot a couple of times. But this is a nice combination because it combines geodata with temporal data and also with graph data. So it combines today's lecture with yesterday. And the data is migration paths between cities in the United States. So overall, you could imagine that there would be edges. So like for each person moving between a city, there will be an edge, or there will be like or rather, like to put it another way, so there will be edges between all of these nodes, and the weight of those edges is going to be the number of people moving between the two cities. That will be the base data. But of course, it's a dynamic graph, so that's the temporal aspect. So this pattern moves over time. So you can select the time frame, and that will of course reweight the entire graph, or maybe even make some of these edges disappear. So if you select a small time frame and there was nobody moving from here to here, then the edge would disappear altogether. And obviously, this graph, if you would draw it in full, maybe on top of the map of the United States, it would be super cluttered. So what they do here is they provide a very nice advanced way to tackle this situation. So you can select the areas of interest where you really want to see the movement patterns. So you kind of restrict the cities that you want to judge. So here we see Washington, the state, which is here, California, New York, and this is called the Liberty area, the orange one. And the B visualization, so we visualize it on the map, of course, and we have this simple but very powerful visualization of on the right side, which is spatially abstract, where it's simply a graph itself, and here we see a nice histogram over time, I believe. We see movements within the area, so we see that there have been lots of people moving between cities or towns within New York, but the pattern is completely missing from California. So there have been no movements in the selected time frame. We see some immigration from abroad to the Liberty area, and you can see that they provide a lot of tools to really tackle this advanced data. They are also working with scented widgets, so you can filter the data by various attributes, which can be related to both the but I think it's related to on the town level. So you can see you can have like age distribution, crime, which county it is from, this categorical data, and so forth. And the selections are up to you. So these selections are of course user driven. So you can draw the rectangle pretty much any way you please. So of course, this is not let's say knowledge that you have to remember what Van den Elzen system did, but I really wanted to show this as a masterclass in pretty much all aspects of InfoVis, because they have very complex data, geo plus temporal plus graph, and everything is weighted, typed, and attributed. So a rather complex data set, and they have chosen the visualizations well. They have very good multi-view design. Things are connected. It's very clear what you're doing. They have capabilities for aggregation and zooming, which is both semantic and smooth. So if you remember what we have talked about yesterday with the smooth navigation, so the smooth navigation capabilities are implemented in this system. And all 7 interactions are done well. So those are the select, explore, filter, abstract, elaborate, and etc. Those are done very well. So if you're interested, you can watch the demo of the system on following the YouTube link. And this is a very nice example of how complex data can really come together in a nice system, which was indeed awarded a prestigious prize by the InfoVis community. So it doesn't seem to be just my opinion, but the general community opinion. So well done to these guys. Okay, so this has been a bit of a shorter lecture. To conclude, if you're working with graphs, I repeat the pipeline. So we're going from graph through analysis through filtering to visualization, but of course we can iterate a bit. So filtering the graph can result in a new graph to be analyzed, and filtering and analysis often go hand in hand, because of course. I mean, I didn't repeat this really explicitly, but I mean, in order not to sound like a broken record, but you know, we don't want to distort the data. We want to show faithful representation of the underlying data, which can be complex. So analysis and filtering should be done together, and we shouldn't overfilter and show some kind of trivial reduced graph or even worse, a graph that is manipulative, so we completely distort the structure. So this needs to be done right. I mean, of course, there are underlying graph theory algorithms that are beyond the scope of this course. That's a bit of a problem with this course, that we cannot really give a primer on the actual data science, data analytics, data analysis rather. There's no time for it, so we kind of assume that you know all this, but because it's only about visualization. But yeah, it's really key. So graphs are very often too complex to visualize on the screen, and if they are easy to visualize directly, then then they are trivial graphs in the first place. Do we have a question?
Yes, Lianson asks,
Absolutely.
how useful are tree visualizations for data exploration, gaining insight into data?
So, I would like to ask you, could you maybe clarify the question a bit? So because the kind of the trivial answer to this would be well, if you have tree structured data, then you need a tree visualization to be able to delve into the data, right? But did you perhaps mean it in another way? I'm not sure I understand correctly. If you could elaborate a bit.
VA system versus InfoVis. He says, but maybe otherwise he can ask it. I don't know if I click
right. Yeah. I mean, I will attempt to answer the way I understand it, and if I have answered something different and you have further questions, then let me know, of course. Well, so I think they are definitely very useful, right? So if you have because graph data are very common across many phenomena. So we have discussed that visual analytics is all about domain specific data sets and domain specific knowledge that is being extracted, and basically lots of those data sets are graph, right? So that's the nature of the beast. So then you will indeed need to delve into the trees. And I mean, I would actually say that any visual analytics system, or like any advanced or one, basically every time you want to implement abstract elaborate, you kind of need a tree, right? Even if it's not directly visualized on the screen, you need a tree, because you will have basically the generic zoom level, then you're going to have zoom level 1, zoom level 2, zoom level 3, etc. So that's a tree already, where you're kind of clumping parts of the data together, and you're kind of splitting it. So you have this, and plus you have navigation, so that you can jump on the same depth depth of the tree to other parts of the data set. But yes, lots of phenomena are graph/tree based. So generally, what is important here is that is the part about the compound graphs, right? So even if you have a generic graph, then it's useful to because the tree visualizations are a bit more plentiful and a bit more understandable, because they provide a nice level of abstraction/elaboration, right? So they're kind of tied to that. So you start at the root level of the phenomenon, and you kind of expanding to the detail. But if you have a generic graph, then you don't really know where to start, because you don't have a root node. Everything is connected with everything. And if you select a node at random to start your exploration, then are you actually selecting something useful? So if you make a compound tree out of it, so maybe you found a minimum spanning tree, and then you use that minimum spanning tree to place your visualization, or to place the various sections of your graph on the screen. Then you impose a meaningful structure which is grounded in inherent properties of the data, so in the actual weights of the edges, and then you can work with it further, and this will kind of glean some insight into the structure of the complex data that you wouldn't be able to disentangle yourself. And then you do the clutter reduction techniques, / you select the right tree visualization, etc., etc. So a bit long-winded answer, but I hope that there was something useful in that. Yeah.
Yeah, he says thanks, and I don't see any more questions, to be honest.
Okay, but I'm going to finish with the last slide of the conclusion. If there are questions, then feel free to write them, of course. But really, just to conclude, there's a large variety of methods, especially for trees. So I recommend Treevase, the link I have given a couple of slides earlier, to inspire yourself to really see what can be done with trees. There is a strong relation to graph theory and graph analysis algorithms. It's a necessary part of the pipeline beyond trivially sized graphs. Well, it not that it only combats computational complexity and clutter, but it will also help you identify the parts to display. So so even the simple example that we have given about computing the degrees of nodes, and you just rank the nodes by their degrees, will already give you some insight into which nodes are important or connected to a lot of other ones, and which ones are a bit more isolated. So it's a bit of a challenge to really understand or to really analyze fully complex graph data rather. Sorry, but there are tools to help you there. And note that I think that in the text analytics lecture, which is coming up next Monday, we're gonna see a couple of, I think there are a couple of examples there where you are gonna see graphs being used for working with text. So for instance, if you have a topic hierarchy, so you detect topics from your text, those typically have a hierarchical tree structure. So that is already something that and then of course visualizing that is the domain of tree visualization, even though you have worked with text data. So you can find graph style relationships in many other domains. So hopefully that this will shed some additional insight. So thank you for coming to the lecture. One last call for questions.
I think we discussed all the questions. I don't see anybody typing either.
Very good. So if there are further questions, then hit us up in the Discord. I'm going to answer everything. And thank you again for coming. And I'm going to see you next Monday. Bye bye.